For lecture 26 on the proof complexity as a computational lens course. We're talking about cutting planes today again, which we all know, but we want to use the configuration style definition of cutting planes where we care about both length and space. So let's go over it quickly. So I'm presenting the proof on a whiteboard or blackboard where I can, at any time, I can copy constraints of my input, which we'll think of today as a CNF formula, but translated to a linear inequality, just sum of the literals greater or equal 1. So I can download an axiom. I can also download at any point a variable axiom saying that x lies between 0 and 1. Then I can imply inference rules, but only to constraints that I currently have on the board. And then I can erase stuff that I don't need. The inference rules are, and the goal is to derive 0 greater or equal 1. The inference rules are, well, the variable axioms are probably axiom rules, but as we said, variables are between 0 and 1. And then you can add two valid linear inequalities. You can multiply by a positive number. And if the linear form on the left-hand side is divisible by a positive number c, then you can divide through by c everywhere and then round up on the right-hand side. And we care about two complexity measures. I think today, you could care about more complexity measures, but we care about length, which will be the number of constraints you see in a derivation. And if you want to be really precise, then we're going to count this with repetition, though it won't matter too much for us today. It does matter because sometimes you maybe throw away a constraint and then because you're tight on space and then you'll rederive it later. So that's why we're counting with the repetition. And then we'll measure line space, which is just the number of linear inequalities you have in memory at any given time. This is what we care about today. One thing that we haven't talked about, except briefly, is what about these coefficients? So we're interested in how large are they? And you can also think a little bit about this rule. So Cook, Couillard, and Turan in '87 defined this proof system. And then building on this, Buss and Clote made two nice observations. So the first observation is that the division rule, we're stating it for any positive integer c. You can actually fix your favorite integer c, like 2, 3, 4, 5, and then just define cutting planes with only cutting planes with division by 42 only. Okay, that's a proof system. And it turns out that this is polynomially equivalent to standard cutting planes. It gets a little bit more cumbersome, but you can, without more than a polynomial blow up, you can still do anything cutting planes can do. And then Buss and Clote in '96 used this to prove something more interesting. So again, this is Buss and Clote, '96, and building on the original cutting planes paper. So they proved the following. So suppose the coefficients and constants in the input, so look at the input, and suppose that they have absolute values bounded by some v. Okay, so meaning that essentially we can represent anything in input is in log b bits. Okay. And suppose that pi is a cutting planes refutation of f, which is now, this is not just CNF, this is like any integer linear inequality, but in particular for CNF, b would be very small. There's a cutting planes refutation pi of f in length L. Okay. Then there exists a refutation pi prime. And the length of pi prime is at most a polynomial blow up. So L cubed log b, and the coefficients and constant terms. Let me just write coefficient, but like all the integers appearing here actually have absolute values. All the coefficients have absolute values bounded by L squared times b times 2 to the f. Okay? Meaning, with at most a polynomial loss in reasoning power, the number of bits that the number of bits that I need to represent any constraint in my refutation is polynomial, meaning that the magnitude of all the coefficients and constant terms are at most exponential. So without loss of generality, cutting planes only needs a polynomial number of bits or exponential magnitude of coefficients and constant terms. Dadouche and Tivari also proved that this holds for stabbing planes. Now, if you read the Clote paper, they were actually shooting for something else. They were shooting for polynomial magnitude. They were shooting for, meaning a logarithmic number of bits. And the question is, so what we're asking is, basically, is it possible to bring the coefficients down to polynomial magnitude? Down to polynomial magnitude. Meaning a logarithmic number of bits. This is still open 30 years later. It's not even clear what separating formulas would look like. So I asked some very senior experts, I had some email correspondence this last week, trying to understand, like, what's the lay of the land? Do we even have candidates? And I don't think, it's worth thinking about, like, what would, ideally I'd like a CNF formula. I mean, but really anything, like, what would a separating example look like? Can we think of anything like when would cutting planes with unbounded coefficients be used? So formally, I can define cutting planes. The usual notation is CP star. So CP star is as standard cutting planes, but in any derivation, the coefficients and constant terms have size poly in the size of the input. Okay, meaning again that in the logarithmic number of bits. I should say that there are two slightly different definitions of CP star. It doesn't really matter. The way Bus and Clote did it is you actually allow the coefficient to scale with the length. So in their definition of CP star, like a CP star proof that is exponentially long, then basically you're removing the restrictions on the coefficient. I think for us, I mean, it seems like more natural maybe to fix this to be a property of a refutation related to the input. It doesn't really matter in the sense that we're trying to pin out what CP star can do in polynomial time, and then except for lower order terms, it's kind of the same. Okay. So the question is, can we separate CP and CP star? That's the question that remains open. So then we can relax and say, well, can we think of anything that cutting planes with unbounded coefficients can do that CP star cannot? And it turns out that, well, as far as now, there's one thing we know. And that's what we'll talk about today. So there exist CNF formulas such that, firstly, cutting planes, general cutting planes, refutes Fn in simultaneous length n squared and line space constant. Sorry, that's a constant. Note that line space constant is not so impressive. We know from before that you can do anything in constant line space, but note that we're doing this in constant line space and also polynomial length. To be really precise, let me add a tilde here, meaning it's something like n squared times some polylog factors that between friends we won't worry too much about. However, CP star cannot refute Fn in sub-exponential length and subpolynomial line space simultaneously. We'll make this more precise later with parameters and so on, but this is like the gist of it. So what does this mean? This means that we can exhibit a family of CNF formulas that for CP star, they exhibit some kind of trade-off behavior. For cutting planes with unbounded coefficient, this trade-off behavior is gone. Does this make sense? Okay. And the main technical ingredient, which you have maybe guessed, I mean, we've had a bunch of this. We're going to do this via a lifting theorem. And we're going to use a new gadget that we haven't talked about before, the equality gadget. Getting a little bit ahead of ourselves, what is the equality gadget? Well, the simplest version is Alice gets 1 bit, Bob gets 1 bit. The equality gadget is true if the bits are equal. It's false if the bits are not equal. You can generalize this to bit strings of arbitrary length. Again, the gadget is true precisely when the bit strings are equal. It's false otherwise. Yeah. I should say that there are several things you need to do. You also need to come, like, what do these formulas even look like? This is this is going to be the heavy technical lifting, but something that is maybe not so heavy technical lifting, but is still worth thinking about for 15 seconds before I reveal it to you. Again, even, what would a formula that has this probably look like? How can you expect cutting planes with unbounded coefficients to save space? Okay, so here's the idea. So I'm kind of trying to argue that actually you need a good idea, and then you need a lifting lemma. I'll basically just tell you the idea, and then actually you have to check that this idea works, and this is some technical work which we mostly won't skip, because we'll mostly skip this and then we'll focus on the lifting theorem, which is even more work. But here's the idea. Okay. So take a Horn formula. What is a Horn formula? A Horn formula is a formula where every clause contains at most one positive literal. Okay, a Horn formula is a CNF formula in which every clause contains at most one positive literal. Now, either a Horn formula is satisfiable, or if it's unsatisfiable, then basically one thing that's going to the Horn formula will have some unit clause, a clause of size 1, containing only a positive literal. Because if all clauses are of size at least 2, then an all false assignment is good, right? So an unsatisfiable Horn formula contains a positive unit clause. And basically what you can do is just propagate on these positive unit clauses, simplify the formula, keep going. And this you can do in resolution. So in technical terms, for those of you on the SAT solving side, Horn formulas are solved by unit propagation in resolution, meaning that they have very simple proofs. So basically, there is some topological order, say, of the variables where you just derive that Z1 is true, Z2 is true, Z3 is true, all the way up to some Zn, and then you run into conflict with that Zn actually has to be false. Okay? So basically, let me write this. So what will a resolution refutation look like? Well, if I relabel the variables, I basically derive Zi in some order I, 1, 2, 3, and then I hit a conflict with not Zeta. Okay? So how would I do this? Well, here's the thing. In cutting planes, what if I take all of the variables that I've derived so far? From I goes from 0 up to j. Actually, let me index the, just for simplicity, let me index the variables from 0, 0, 1, 2, up to n minus 1. I'm going to switch back to 1 to n before, but it's just nicer to write now. So suppose I have derived that Z0, Z1, Z2 up to Zj are all true. Then one thing I can do in cutting planes, definitely, I can just pack this together into just two constraints. I can write the constraint 2 to the I times Zi equals some I goes from 0 to j, 2 to the I, which is just 2 to the j plus 1 minus 1. Right? And note that this, I'm writing equality here. We know that this is just syntactic sugar, like linear form equals constant. That's just, for me, that's syntactic sugar for a pair of inequalities. Linear form greater equal constant, and then minus linear term greater equal minus constant. Yes? And so now the idea is, so for any Horn, this means that if you now work out the details, and this is what I'm going to skip, I claim that for any Horn formula, cutting planes will have a refutation in almost linear length. And everything that is true so far, you just pack it into two constraints. And now you have to think a little bit about, okay, when you, every new unit clause that you're going to derive, you'll need to somehow see which true literals you need to use to derive this. So you'll have to be able to, like, everything that you derive is true, you tag it onto this constraint, but that's easy. And then you'll also have to, at times, you'll need to be able to, if you have this big form and you're interested in Z42, then you need to be able to extract that Z42 is true. And you should think about this. But it turns out that these kind of extraction can be done efficiently thanks to the division rule. Planes can do this. This requires an argument. Okay. And now here comes the, but of course, Horn formulas are very easy, so we won't be able to use those. So here comes the idea. We're now going to use the equality gadget, which again, we said that this is 1 if the bits x and y are equal and 0 otherwise. And I'm going to substitute my formula with the equality gadget, and just to make absolutely sure we're on the same page. So I'm sticking with the convention we've had in the last few lectures that somehow the unlifted formulas live over z variables. And then you all know that, you know, a communication problem will arise pretty soon, and Alice and Bob will have access to x and y. So then when I lift this with equality, in our previous notation, I would lift this with equality. In the Gus et al. Notation, we'd write this C composed with equality. This will now be, if you think about it, this will be, so the fact that Z should be true, this will give you this. Let's see if I can get this right. Just to make sure we're on the same page. So this is the lifting of Z1, and Z2 being false is this. Actually, I wonder if I switched them. Did I? Think about it quickly. I think this should be maybe lifting this false. Let's see. So I claim that no. Let's see. So C should be true if Z is true or Z1 is true or Z2 is false. No, maybe it's fine. So if Z1 is true, then when I lift, I want X and Y to be the same. If X and Y are the same, then these clauses will make sure that the whole CNF evaluates to true. If Z2 is false, then X and Y should be different. And that will make this part of the formula evaluate to true. Yeah, I'm always confused about this, but this I think was actually correct. Okay, so now the point is take a Horn formula, substitute it with the equality gadget, and now you think about it and you realize that I can still sort of pack truth value assignments into forms like this. Because again, the fact that a literal Z is true is just saying, okay, so maybe let me write it down. So now what I'm going to sort of the fact that Z0 up to Zj, they're all true. This in the lifted world, this will correspond to, intuitively, this should correspond to I goes from 0 to j, 2 to the I, xi minus yi equals 0. Is this making some sense? And now I have to think about, okay, can I still like sort of derive these equalities one by one, tag them onto this growing exponential sum? And can I decode when I need to know that x42 is equal to y42? This requires an argument, but the answer is, like you sit down and do this carefully and you will get it to work out. You do incur, like the original, in some sense, the resolution refutation with unit propagation that you're simulating runs in linear time. We're picking up something slightly super quadratic. That's because of the encoding and decoding steps. Okay. Again, this requires a proof, but this means that basically for any Horn formula I substituted with the equality gadget, I will now have a CNF formula that has a short cutting planes proof in constant line space. Are we happy with this? Good. So now the point is that why we might be in business is that clearly these coefficients will in general have to go up to size 2 to the n. And CP star cannot afford this. So now we're going to say, okay, so like suppose there's a CP star refutation, pi star of the formula Fn, which is this, let Fn is some Horn formula over n variables. And suppose I compose this then again with the equality gadget. And now there's a CP star refutation of this, which I call pi star. In length L and line space S. Then we know before that what can Alice and Bob do? Well, when we did cutting planes trade-offs, we said that this deals a communication protocol. In general, we needed what did the communication protocol do? It did binary search in the proof to find a transition from, given alpha, assigning variables to xi and yi, we wanted to find a falsified clause. And the way Alice and Bob did this, they were given alpha, they just evaluated the blackboard configurations and found the transition from true to false. that was an axiom download that's a valid answer to the falsified clause search problem. We needed this in real communication. Why? Because Alice and Bob needed to evaluate linear inequalities, and you could have very, very large numbers. But now we're in CP star, so actually Alice and Bob can just evaluate their part of the linear inequality. Say Bob moves his part over to the right-hand side, and now we just want to know, is Alice's part larger, equal than the constant term minus Bob's part? These are polynomial magnitude numbers, so Alice and Bob can just, with standard communication, actually send the integer bit by bit and then compare. Yes? So if there is a CP star proof in length L and space S, then this yields a standard deterministic communication protocol for the falsified clause search problem for F composed with equality. How much do Alice and Bob need to communicate? Well, they need to communicate roughly, they need to do binary search, so that's log L steps. And then for every blackboard, they need to evaluate S inequalities. And then there's going to be some kind of, I don't know, some kind of log n or maybe log square n or something like this. Okay? So this means now that if we can prove so now obviously we want to do a communication lower bound. We want to find a formula for which this composed search problem is hard. And we know how to do this. I mean, we've done lifting theorems. We can, so we want to now we want to prove, if we can just do this, we might finish early today. We want to prove that the deterministic communication complexity, which I'll write d to the cc, of this search problem for f n composed with equality. I want a lifting result that says that this is, well, there are going to be maybe some slack there, but roughly this should be the decision tree complexity, the query complexity of a deterministic decision tree that just solves the usual search problem. Right? This is what we have now done, kind of. We did this for cutting planes when we did size space trade-offs there. And then we kind of did this, except we didn't do it for decision trees. We did it for decision DAGs, which was this decision tree quote unquote model that corresponded to general circuits, to DAG-like communications. Okay, so suppose we can do this. So now we just need a formula family that should be ideally a Horn formula family and should have large decision tree complexity. Do we have a candidate Horn formula that has large decision tree complexity? We sure do. Pebbling formula. Like we have analyzed the complexity of pebbling formulas before. We know that if we plug in the right pebbling formulas, then they have large decision tree complexity. Okay, done. Right? It's like clear. If we can implement this, then we're done and we can go home. Yes? There's only a problem that so such a lifting theorem is known not to be true. It cannot be true in general for the equality gadget and for search problems, also known as relation. As opposed to, like, again, we know that before we had other gadgets, but now we're taking the equality gadget. which is a trickier gadget. And also, again, the falsified closed search problem is a relation. It's a search problem. It's not a function. And if we just have picked another gadget, or if we would have had a function, then maybe we could have proven a lower bound. But if you want to do the equality gadget, and if you want to do a relation, then it is not true in general. And this is a result of Bruno Loft and Shagnik Mukhopadhyay. In 2019. So it's interesting. It's interesting to note that before what we did, like once we got this far to the composed search problems in all our previous, not true, but okay, I'll take this back. In our first lifting theorem, we didn't really care about that we were lifting a falsified closed search problem for CNFs. In our second lifting theorem, the one that Kilian did, we did care a little bit more, but somehow it wasn't, I'm not sure how important it was. Here it's like, but at least in contrast to the first cutting planes lifting theorem that we did, so it won't be true for any search problem that you can do this. It's just false. Okay? So if we want to do something like this, we need to do something different. Or maybe, meaning that maybe we need to go a bit under the hood. And there are two things that we're going to do differently. And then we're going to spend the rest of this lecture talking about this. So what we will do we're going to use the equality gadget over any number of bits. So we get to q-bit strings, where in general q will be larger than 1. Q will even be non-constant. Still the same definition. The equality just checks whether these bit strings are coordinate-wise equal. If they are equal in all coordinates, then the equality gadget says 1, otherwise it says 0. So we're going to lift with a larger gadget. But now you realize not too large, because our CNF formulas will blow up now if we do this. And then what we're going to lift is we are going to lift the Nullstellensatz refutation degree. So we're actually going to say, I'm not looking at any search problem. I'm going to look at a falsified CNF formula search problem. And I'm going to lift the Nullstellensatz refutation degree complexity of this problem. And then we will be in business. Okay, how does this change our use of pebbling formulas? Not really, because we know that actually for pebbling formulas, the decision tree complexity and the Nullstellensatz degree coincide. Meaning, in particular, pebbling formulas will still be good candidates for us. But we will have to argue differently when we do the lifting. Instead of just arguing that we have a decision tree lower bound, we'll somehow have to argue about a Nullstellensatz degree somehow. This is going to get fairly technical, and I hope to be able to tell you a story of how the proof goes, and do some of the details, but not all.
Okay. Can I ask about what is written on the right board? Is like the cos s log L times log n. This log n is just the coefficient for the coefficient size.
Yeah.
So the statement is also true for general cutting planes. If you write something like log.
I mean, for general cutting planes, we would then before we used real communication, and then there was no log. Then we just had this. In real communication, Alice and Bob could send just any real numbers. So then they didn't pick up this cost. Yeah, that's a good point. So because a priori in general cutting planes, I mean, this could be exponential. And again, in communication complexity, the name of the game is we're somewhere in between constant and linear. And so communicating in a standard deterministic communication protocol, sending exponentially numbers of exponential magnitude is like, then everything breaks because there will always be linear upper bounds. Yeah, so this is like, as Dori was asking about, this thing is like the CP star part. And this is because we're using deterministic communication. If we knew that we would, before when we analyzed general cutting planes, we got only this, but then we needed a stronger model. Then we needed the real communication model. Make sense? Good. Okay. So that now what we're going to have is something like the following. And there are going to be a lot of things that throughout this lecture. So let me state the first version of the main lifting theorem. Again, we do need you need to be a little bit careful now because we're going to lift with gadgets of non-constant size. And you now need to think about what is going to happen with your blow up. Can we still do the upper bound? And the answer is yes, you can. And it's important to write up the details, and it takes a few pages, but you sort of, I mean, we have the idea. Nothing more happens. Just careful bookkeeping, and this works. So the fun part from now on, like the idea, the important thing for the upper bound was getting the idea that, oh, Horn formulas plus the equality gadget seems like a good idea. That was like the creative thing. And once you have that, the upper bound is kind of fun. And in fact, this idea was lying around for several years before we finally had the lower bound that was missing, which is generously contributed by Robert Robere and Tony and Pitassi. We'll get to that. So the main lifting theorem, which is mostly due to them, is saying that suppose that f is a, for now, let it be a minimally unsatisfiable CNF formula over n variables. We'll relax the minimally unsatisfiable condition in a bit, but let's keep it for now. So this is f is always, for the rest of this lecture, I'm going to run out of energy typing. F will always be an unsatisfiable CNF formula over n variables. Always, always. Okay? F is always, bold F is going to be any field, your favorite field. Spoiler alert, I guess we don't care that much because we know for pebbling formulas it doesn't really matter. For the lifting theorem, it does matter. We'll let G be any gadget, so any function that maps x product y to 0, 1. And when I do so, I can think of G as defining a matrix. Just consider a matrix with rows indexed by x, columns indexed by y, and in every cell, lowercase x, lowercase y, I just evaluate the gadget G. Okay, in particular, what will I get for the equality gadget? The identity matrix. Yes? Okay. So the rank of the gadget will be the rank of this matrix. And I want the gadget to have somewhat high rank. We're going to say that it should be some constant, which is 6, times e, base of the natural logarithm, times n, the number of variables, divided by the Nullstellensatz degree of refuting f. And just to carry this around, let me write the superscript f to say that we're in the field f. Because this is like where we're taking it around. So suppose that G has somewhat high rank. There's a trade-off here. The better the Nullstellensatz degree lower bound, the more relaxed I can be about the rank here. So you should think of we're going to have our Nullstellensatz degree are going to be something like roughly n log n. So I'm going to be shooting for rank log n, something like this. Okay. Suppose I see in a formula f a field both f and the gadget G like this. Then I claim that the deterministic communication complexity of solving the composed search problem for f composed with the gadget G is going to be at least the Nullstellensatz degree of refuting f over the field both f. This is the lifting theorem. This is the main technical challenge that we have. And then just to write down, what do we need to prove? Then we need to prove an upper bound for general cutting plates. So in addition to what we've said before, G is now any constant fan-in DAG with a single sink. That is, it's the kind of graph you would do pebbling on, right? Let Q be an integer, and let me choose the scaling. Q will be log n, where n is the number of variables. Okay. Then, if we look at the pebbling formula over G, composed with the equality gadget of arity Q, this is again the same thing. I mean, before we used also the notation peb G and just plugging in equality Q. These are just two notations that mean exactly the same thing. This is like the same formula, depending on which notation you like better. What do we know about this formula? It has something like, n log n variables. It has roughly a linear number of clauses. And the width that you're going to pick up is basically your Q. So the width is going to be log n. And this formula has a cutting planes refutation in simultaneous length n squared, except for polylog factors, and line space constant. Okay, how do we prove this? The way we talked about it before. And now the lower bound this is the upper bound for CP, then we get a lower bound for CP star. This is basically just going to be this lifting theorem. Okay, if we plug in this lifting theorem and we use the fact that a short space-efficient refutation with small integers give us an efficient communication protocol, then we get that any CP star refutation pi star in length L and line space, line space S, will have S times log L, essentially the communication complexity will essentially have the Nullstellensatz degree, so n over log n. Except here you should also, we'll need some extra communication for the integer, so we pick up a log square there. So if we can prove this lifting theorem, then this lower bound is pretty immediate. I claim by just doing things we've done before. The upper bound, we sort of talked about what to do with. What's the idea? Just you're going to carry around actually just two inequalities, and you're going to pack. Basically, you're going to work on your pebbling formula. For every vertex in topological order, you just derive that all of the, there are going to be two q variables, xi and yi per vertex. You start at the sources where the source axioms say that these are coordinate-wise all the same. And then you just use your pebbling axioms to derive this for the whole formula in topological order. And then with some careful bookkeeping, these bounds are what you get. The lower bound follows immediately from taking a short space-efficient proof with small integers and using it for Alice and Bob to build a communication protocol for this problem, and then plugging in the lifting lower bound. So this means that all we need to talk about is the lifting. Okay? And the interesting thing, I think, is worth pointing out that it's really important that we use a good gadget here. Like, why couldn't we do this with the lifting gadget, for instance? Well, the point is that we know that we want a gadget that will lift and give us strong lower bounds for deterministic communication. But suppose there's also randomized communication where Alice and Bob can have a public source of randomness, and they can use it to flip coins, and even flip coins in a coordinated fashion. There's real communication where they can send real numbers of arbitrary precision and have a referee compare them. If we would have a gadget like the indexing gadget, for instance, then that would also be hard in this setting, but that would imply that would imply lower bounds for general cutting planes. So then the formula would become too hard. We want a gadget that strikes at CP star, but leaves CP alone. And the equality gadget has exactly this property. If you think about the equality gadget, if you lift something with equality, for randomized communication, we know that you basically, if Alice and Bob need to check whether their bit strings are the same, there's a very efficient, basically hash-based protocol where they do random hashes of their bit strings, and if the bit strings are separate, then just after a few hashes, you see this with overwhelming probability. For the real protocol, Alice and Bob can just compare their bit strings viewed as numbers. So with just 2 bits of communication, they will know if they have exactly the same bit string. So the equality gadget doesn't make life harder in a randomized communication setting or in a real communication setting, but it does make life much harder in a deterministic setting, because there's a classic result saying that, like, the first problem you learn is hard for deterministic communication is this very basic problem of Alice has a bit string of length n, Bob has a bit string of length n. How can they decide whether the bit strings are the same? And the answer to this is, we know actually for deterministic communication that the stupidest thing you could think of is optimal. Namely, the optimal protocol for this is Alice sends her bit string over to Bob, n bits, and then Bob sends a bit back saying we're equal or we're not equal, n plus 1 bits. We know that you cannot do better than this for deterministic communication. And this is why this is somehow the right gadget. So so now we're going to get into technical details. Before we do so, let me just talk about some open problems. The most obvious open problem, the one we started with, is a size separation for CP versus CP star. Okay. I think it's nice. Again, I want to stress that. So what are we now? I guess we're 40 years after the definition of the cutting planes proof system. And also there are other proof systems out there that use real values, right? Stabbing planes and so on. Like in no setting, as far as I'm aware, in no setting, I mean, we do have, again, for both cutting planes and stabbing planes, we know that we can bring coefficient magnitudes down to exponential magnitude without loss of reasoning power, except for polynomial. We do not have any understanding, I think, in any proof system, to the best of my knowledge, below this. Like, can we go down to logarithmic planes? We just don't know. Again, Bass and Clote, reading their paper, they seem to believe that, yes, we can, but they didn't quite get there. Okay? So after first, now I guess in view of our papers, we're sort of providing some circumstantial evidence that no, maybe CP and CP star are in fact different. We don't know, but after 40 years, this is at least like, I think for any proof system that we know, this is like a separation of sorts between low weight and high weight coefficients. So I guess I'm trying to sell this result a little bit. Like it might look, I don't know, depending on what your mood you're in, like, were we really looking for a length space trade-off? Is that the end of the line? Hopefully not, but it's at least something. And this is the strongest result we have. But of course, we were looking for a size separation. Is it true that cutting planes can refute things efficiently for which CP star requires super polynomial length? This remains open. I think it's a great problem. But again, the first challenge would be to even come up with, what would a formula look like? Another thing that will become clear. So actually, the pebbling formulas that we're going to plug in to get this will just be coming from graphs for which we have unconditional space lower bounds. So actually, the fact that it looks like this, is not because the pebbling graph as such has a trade-off. This is different from what we had before. When we did lifting a few lectures back, we actually had trade-offs over on the pebbling side. For these formulas that we're going to plug in here, we don't have any trade-offs. And this raises the question whether this log L is just sort of an artifact of the proof. Maybe if we worked hard enough, we will get line space lower bounds for CP star. We don't know how to do this, but in some sense, we do know that such line space lower bounds do not hold for general conic planes, but we do know also that the upper bounds that we know of need coefficients of exponential magnitude. So it's conceivable that maybe this result is a CP star line space lower bound in disguise. Related to this, could we actually prove true length space trade-offs for CP star? Where I mean that they shouldn't apply to general cutting planes, right? We do have true trade-offs for general cutting planes. Could we have this same result with the upper bound and the lower bound, but actually exhibit formulas which do have proofs in small line space and small length, but not simultaneously for CP star? So just to be clear, these formulas we're exhibiting now, we don't have any small space proofs for them, and we don't believe that they have such proofs. So this would be like an interesting strengthening, and I think this is might well be within reach. But related to this, would be some way of proving, getting a more direct lower bound technique for parity decision trees for pebbling formulas. Because one thing that pops out of, I haven't said what the paper is. So all of these results are from, this is by Did I forget this? This is by Susanna Rezende. This is by Or Meyer, myself, Tony Pitassi, Robert Robere, and Mark Vignos. Building heavily on an earlier paper by Tony and Robert, and on Robert's PhD thesis. So one thing that comes out of this paper is that was for the first time where we see that reversible pebbling price and decision tree complexity and parity decision tree complexity, these three measures exactly coincide for pebbling formulas. The proof that this is so is very roundabout. It would be interesting to get a very much more hands-on lower bound that parity decision trees, when applied to pebbling formulas, that they do have, that the lower bound is the reversible pebbling price. Why is it interesting to have a more like concrete lower bound on this? Well, because probably, if you think about Alice and Bob and they get this search problem, the lifted search problem over here, what would they do? Well, one thing that they can do, if you think about it, is if they have a good parity decision tree, then they can simulate parity decision tree queries. And this will be helpful to, like any parity decision tree that solves the original pebbling problem can be lifted to solve the problem also for pebbling formulas lifted with the equality gadget. You need to think about this maybe for a few minutes. But so in particular, this means that because I'm using the equality gadget, it's always true that that decision trees give Alice and Bob a good strategy for a protocol. But because we're using the equality gadget, they can use a stronger decision tree model. They can use parity decision trees and make progress, and that will give us good protocols for pebbling formulas lifted with equality. For all we know, these protocols might be the optimal protocols. And so if we really want to have a finer understanding of the deterministic communication complexity lower bounds, in particular, suppose that I promise Alice and Bob are using a parity decision tree and they're simulating this. Can I somehow give a concrete, more algorithmic simulation-based lower bound, like how would I, if I want to show parity decision tree lower bounds, can I give a concrete strategy for answering queries from a parity decision tree to delay defeat? We know how to do this. We can play this game optimally, like in an online setting for standard decision trees, for parity decision trees, we don't know. So these are our four good questions related to that I want to highlight, and I do it now because towards the end of the lecture, maybe we're going to be so tired that we're going to forget about this. I want to set up some technicalities. I'm thinking I'll go on for a few more minutes and then we'll have a break probably. So just to recap, where are we now? So now we're just going to talk about the lifting problem. So the search problem, yeah, just to recap, what do we have? We have some kind of input domain. We have an output domain. And the search problem is the following. We're given a Z. We want to find, so a Z living in the input space. We want to find something living in the output space so that Z, comma O is in the relation, is in the search problem. We're assuming always that the search problem is total so that this is possible. Now, we're always going to have like overloading notation a bit. Our input set will always have like a product structure. In particular, from now on, we're going to think of this as being the Boolean hypercube. So the input is like a set of bits. And suppose this is true, and suppose that G is any gadget that maps domains X and Y to bits, then we know that the composed search problem, S composed with G raised to the power of n, where often when n is clear from context, I will start dropping this. This is the search problem. Given X in X, given Y in Y, we want to find an output O such that when I take the gadget and apply it coordinate-wise to X and Y, so again, if I do this just coordinate 1, 2, 3 all the way up to n, then this will give me an n-bit string. So given this is going to be my Z, and I want to find an O such that this lives in the original relation. So this defines the lifted search problem, which we're going to talk about. Where again, just to be absolutely clear, we're on the same page. This notation just means that I apply, this is the string where I apply G to the first coordinate, the second coordinate, all the way up to the final pair of coordinates. Our search problem is going to be, again, before, I said this before, but let me stress this again, the lifting theorems we did before didn't care too much about what S is. Now it's going to be important for us that S is a falsified clause search problem. So what is it? So I to the n is just the n bits assignment. F is an unsatisfiable CNF formula. Given an assignment, we want to find a clause, the index of a clause that is valid. So this is the search F problem. And getting a little bit ahead of ourselves, once I have a search problem, I can always lift it in this way. Now we can also define lifted CNF formulas, which are slightly different objects. These are when I actually plug in the variables in the CNF formula and expand it out. And then I can define the search problem. So what we are going to analyze, we're going to have a search problem, and then we're going to lift it. So this is a lifted search problem. And this is what we're going to prove lower bounds for. But you can also define a CNF formula by just plugging in the variables in the gadget and expanding out. And then consider the search problem for this CNF formula. And actually, a proof from Alice and Bob will give us a protocol for this problem. And now the point is something like a detail that we're skipping over, minor technical detail, is that if you have a good protocol for this problem, then you can use it for this problem. We leave this as an exercise. So from now on, like this is actually what these are the protocols that we get from cutting planes proofs are for this problem, but any good protocol for this problem works also for this problem. So from now on, this is what we're going to focus on. So what is a deterministic protocol for this problem? Well, this is that Alice gets some X in Xn, Bob gets some Y in Yn, and then they know the CNF formula from long in advance. So they've had time to build a protocol tree. What's a protocol tree? It's just a binary tree where every node is labeled by a function, either for Alice or for Bob. So if it's an Alice function, we say that Alice speaks. If it's a Bob function, we say that Bob speaks. And from every node, we have two edges outgoing, 0 and 1. Right? I'm just recapping deterministic communication to be absolutely sure we're on the same page. And if it's Alice who speaks, she will speak a bit that is a function of this input only and not on Bob's. If Bob speaks, then his bit is a function of y only. Okay, but also, I mean, the fact that we're somewhere in the protocol tree means that I can pick a function that depends on where I am in the protocol, obviously. So now for any assignment, any x and y, this means that we start at the top of the protocol tree and the bits spoken by Alice and Bob will define a path until we get to a leaf. And every leaf should be labeled by an answer to the search problem so that Alice and Bob both know what the intended answer is. The cost of a particular protocol is, so the cost of a protocol, pi, is just the longest path. Because that's the worst case amount of communication Alice and Bob might need to do. And then the notation that we're using for a problem, suppose that P is some kind of communication problem, that I'm using the notation, the deterministic communication cost of P, and this is the minimum overall protocol solving P of cost, all protocols pi solving P of cost pi, right? This is the quantity we're using. And then again, so as I said, suppose that G will always be this gadget X over the product space of X and Y. The rank over F of G, I just define it to be the rank over F of the following matrix. So I just have basically all possible inputs. And I just plug in cell 1, 1, I evaluate X and Y on the first input. First column and second row, I evaluate on X2, Y1, etc. And here, I guess I evaluate on X and Ym. This gives me a matrix. I'll just interpret this over F. Take the rank of this. This is the rank of the gadget. And in particular, I claim now that let me write down this because we're going to use it. So suppose I'm looking at equality over q bits over any field. This will have rank 2 to the cube, which means that since we can find pebbling formulas with rank n over log n, it's sufficient here to get rank log n, which is why I can pick q to be log n bits. Okay, and then we already talked about that if there's a cut and place refutation in small length, small space, and coefficients bounded by b, then we do get an efficient communication protocol. This is just using the communication protocol we had before for real communication, switching to standard communication, and have Alice and Bob transmit their integers in the clear to each other. And the point is that this will not require too many bits. Okay. So we are going to talk about Nullstellensatz. So let's also very quickly refresh our memory of what Nullstellensatz is. So we have switching colors. So suppose we have a set of polynomials which I think over Boolean variables, then a Nullstellensatz refutation showing that these These polynomials don't have a common root over 0, 1. That's just an expression. I find some polynomials qi, which I multiply by the pi's. I find some other polynomials rj, which I multiply by the Boolean axioms, saying that all the zj's should be 0, 1 value. When I do all the calculations and take cancellations, I should get syntactically 1. The degree of a Nullstellensatz derivation is just the maximum total degree of any of these pairs. How do I make this into a refutation proof system? Well, if C is a clause with positive literals Z and negative literals not Z, then actually today we are going to think of 1 as true and 0 as false. So we'll translate this clause C to the polynomial PC, which is just take all the positive literals, they contribute a factor. Every positive literal Z contributes 1 minus Z. Every negative literal just contributes a factor Z. Okay, so with this translation, a CNF formula is just a collection of polynomials, and the Nordström refutation is an expression of this form. Okay, so one thing that I'm not sure if we've said before, but it's something you should know after this course, is how do we prove lower bounds for Nullstellensatz? And the answer is by using D-designs. So what's a D-design? A D-design, capital D, is something that maps polynomials to field elements. It should have the following 4 properties. A design should be linear. It should map 1 to 1. For any input polynomial, pi, and supposing that DAG for any q such that DAG of the degree of qpi is less equal d, the design should map this to 0. So it should map all polynomials to 0, and anything that you multiply the polynomials with, as long as you don't go over the degree bound, should also map to 0. The 4th property of a design is that it shouldn't care about higher powers. So for any polynomial, zi squared times q should be mapped to the same as zq. Assuming, of course, that the degree is not too large. So if q has degree at most d minus 1, then these should be the same. Actually, or maybe degree d minus 2, I guess, if we're be careful about it. Okay. So what can be proven then is, like, why do we care about D designs? Well, because Sambas said that the refutation degree is strictly larger than D if and only if there exists a D design. Okay, so this requires a proof that I'm going to skip, but this is sort of the analog. You can compare the pseudo operation, the pseudo reduction operators that we had before are somewhat similar to this, but we have stronger conditions and we are mapping polynomials to polynomials, not just field elements. So this is sufficient for Nullstellensatz, and then we have the pseudo reduction operators were somewhat analogous, but were stronger objects that we needed for polynomial calculus logarithms. So this allows me to say the final thing, and then we'll take a break, and I'll just give you time to think about this over the break. And this is one result of this paper that, so the Nordström degree over any field of refuting the pebbling formula. So this is something that we're going to need. So the Nordström degree required to refute the pebbling formula is exactly the reversible pebbling price of G. Okay. What is the reversible pebbling price of G? Well, this is, let's define it that again, you can place a pebble on a vertex, or can you remove a pebble on a vertex if and only if all immediate predecessors are covered. Meaning you can always do it for sources. For any other non-source vertex, you can only place a pebble there if all its immediate predecessors are covered. What is your goal? Your goal is to reach a pebbling configuration that includes the sink vertex. Which, since we're using Z today, the sink vertex is sometimes called the target vertex, so we'll use T for the target today. Yeah. So, and here's so what we know is that to prove this, I just need to exhibit a design, and if this lower bound holds, then there has to be a design. Okay, so let me tell you what this is. So let the vertices of this graph be just 1 up to n. So a pebbling configuration is now a subset of the n first integers. And let me just identify that in my head with the monomial Z capital S, which is just the product of all variables Zi for I and S. And now my design is just going to be the following. So fix a positive D. And now I'm going to attempt to define a design. My design is going to be the following. For any monomial, clearly I just define my design over monomials and then I extend by linearity. So for any subset of vertices S, any subset of 1, 2 up to n, I will let the design map the monomial Z capital S to 1 if the pebble configuration S is reachable from the starting pebbling configuration in pebbling space D. Okay, so just pebble away. If you reach a pebble configuration that is reachable without going over the space bound, I'm going to map that to 1. If it's not reachable, I just map it to 0. And the claim that I'm going to leave you with over the break is that this is a D design if and only if the reversible pebbling price of G is strictly larger than D. Okay, so it's an extremely, I mean, it's a very, very concrete definition. I can define this. It's kind of clear. Linearity will be clear. And now you will need to argue properties 3 and 4 that are not so hard. Property 2 is like the interesting one. But this is like an extremely so I don't know. I think this is a very neat proof. You basically you just go over, look at the pebbling formula and verify the details. You go offline for like 10 minutes during the break. You will convince yourself that this is a design. I think with that, it's high time to take a break. Any questions before we do so? And let's have a break. We're back after the break, and we've had time to think about that this is indeed a design. I think, again, I'm saying that this is just really, this is a nice exercise, but I think this is simple only with hindsight. Like, people have been thinking about this. There were partial results about this. There were lower bounds in terms of standard pebbling. And then you look at it in this way, and it's just blindingly obvious once you go through the calculation. So this is I think this is a very neat proof. And I used it also as an excuse to make sure that we've talked about designs, because I don't know if we've talked about this before. So now, meanwhile, during the break, I wrote down exactly what the lifting theorem we want to prove. And I claim that the simplified version that we had before for minimally unsatisfiable formulas follows from this. I won't argue this. I'll leave this as an exercise. So from now on, f is an unsatisfiable k-CNF formula for some k. We will want k to be constant, but we're not saying it here in any way. We'll like take a hit in k, basically. F is any field as before, boldface F. G is any gadget. Let me write, just for compactness, R sub G to be the rank of G. I want this to be at least 3. And also for compactness, let me write D sub F to be the Nullstellensatz degree of refuting F over the field. Then my claim is that the complexity, communication complexity, deterministic communication complexity of the lifted search problem, lifting search F with the gadget G, is the Nullstellensatz degree times the logarithm of the Nullstellensatz degree times the rank divided by the divided by E times N. And here you see that you basically, so you want the rank times the Nullstellensatz degree to be linear in order for this to be something nice. And then some adjustments, you lose 4n times the logarithm of E divided by the rank, and you lose a log in the with k of the CNF formula also. And now if you just work this out, this is like the most general statement, and then you can get this for minimally unsatisfiable k-CNF formulas, for instance, because if you have a minimally unsatisfiable k-CNF formula, then k cannot be too large, because, well, it can't be larger than a number of variables, for instance, things like this. Suppose we're in some Cartesian product space U product V, then a combinatorial rectangle is just a Cartesian product A times B, where A lives in U and B lives in V. For this space, you should think of this, what is U and V going to be for us? Well, it's sort of the spoiler alert, I guess, is you should think of U as being x raised to the power of n, and V is going to be like y raised to the power of n. Is a good way to think about this. But for now, let's be abstract and talk about U and V. So a rectangle partition of U and V is a collection of combinatorial rectangles that exactly partition this space. So any point xy that I take, there's exactly one rectangle that contains it. That's a rectangle partition. Now, a basic fact that we've made use of several times that we haven't proved, this is maybe a good exercise. If I have a deterministic communication protocol that solves a problem over U cross V, then this protocol will yield exactly a rectangle partition. How? Well, just if you look at what inputs end up in every leaf, that is a rectangle, and every input ends up in exactly one leaf. So the collection of leaf rectangles partition the space. This is basically the argument. Relaxing this, I will say that a rectangle cover, a rectangle partition will be fancy style P. A rectangle cover, fancy style R, is just, every point lives in some rectangle, but maybe in many. Like, why do you insist on a partition? Let's relax it. That's a rectangle cover. And I'm going to use that if I have a matrix that lives over this space, and I have a combinatorial rectangle in this space, then I can look at the induced submatrix that is just picking out A on the rectangle R. And I will use this notation A vertical bar R. I will also use the notation if A lives in some product space, as before we can project it to a coordinate or a set of coordinates, just to make sure we have this notation. So then it turns out that a key technical feature that Robert Robere and Tony Pitassi use is the rank measure. Okay. So suppose from now on, fancy style R will always be a rectangle cover. A will always be a matrix living over this. So then I can define the F rank measure, the F rank measure of this rectangle cover at the matrix A. Let me define this. I'm going to use the notation mu sub F, where you could drop the F if we're lazy, of the rectangle cover with respect to the matrix A is going to be the following thing. In the numerator, I just look at the rank of the whole matrix. In the denominator, I take a max over all rectangles in the cover, and I look at the rank of the induced submatrix. Okay. And this is the rank measure of the rectangle cover R at A. This is a measure introduced by Nordström. Why do we care about it? Because if you can get a handle on this, then you can prove deterministic communication complexity lower bounds. You can also prove a lower bounds in a number of other models that we won't talk about. So in particular, everything that we do that we're covering today applies also to other models like span programs that we haven't even talked about. Robert Robere's thesis is actually a highly recommended reading in this regard. So why would this be related to communication complexity at all? Well, suppose you have a really efficient communication protocol, then the rectangles will be very large. Then you could expect that the rank here is roughly the same rank, and then this will be a small measure. Okay. Suppose that I have somehow I get a rectangle cover that I can associate with some kind of protocol, and suppose the protocol has to talk a lot. Then we can expect these rectangles to be pretty small. And if all of these rectangles are pretty small, then just by a dimension argument, all of these ranks will be pretty small. And if I pick the good A, then this rank is large. So it sort of stands to reason that maybe if I find a clever matrix, and if I have a rectangle cover that comes from a really hard communication problem, then this could be large. Kind of, sort of. It's all very intuitive so far. We want to make this concrete. So we're going to say that a combinatorial rectangle R living in Xn cross Yn, where this is the same X and Y as in this gadget. So I'm fixing this notation now. I will say that this rectangle is C structured. What is C? C is a clause in our formula F. Okay, so you remember we had like things being row structured before. I think this is kind of similar. So a rectangle is C structured if two things are true. When I take any xy living in this rectangle and I evaluate the gadget on this, this is a truth value assignment. Okay? This truth value assignment should falsify C. Always. Okay. So basically, again, if we're looking at the rectangle, this means that you are here, C would be a valid answer. Kind of, is the way you should think about this. And also, you could make the argument that C should be the only valid answer, because for any Zi that is not in the variables of C, I want R sub I, so projecting to the ith coordinate, actually covers the full space. So if any coordinate I corresponding to a variable that is not in C, then the rectangle just covers the whole subspace for that coordinate. Then I call it C structure. Okay? A rectangle cover is F structure. If all rectangles are in the cover are C structure. C structured for some C in F. Okay, is this making sense? So here is a key technical lemma that I think we're going to prove. And in my notes, this is lemma 5, meaning I cheated you on, I guess I didn't number the theorems before. Okay, with the assumptions before, like F is an unsatisfiable CNF formula over n variables, G is a gadget, F is a field, right? All of this, I don't want to type this. With these assumptions, the deterministic communication complexity of the composed search problem. Note that I'm dropping the G raised to the power of n here, just because I'm lazy. It's sort of understood from context. This is max over A of min over R of the logarithm of the rank measure of R at A. So where from context you can guess that A ranges over x to the n cross y to the n matrices with elements in F, the field, and R ranges over CNF formula F structured rectangle code. Is the claim clear? Again, so I'm saying let A be living in the lifted space, right? Any matrix living in the lifting space. I'm going to choose this with general elements in F in some clever way. R is going to be any rectangle covered that is F structured. Then I claim that the communication complexity is first I pick the most evil possible A, and then I minimize over all rectangle covers, but I can assume that they're F structured. And then for once I have fixed A and R, I look at the rank measure, and if I can prove that it's always the case then that the rank substantially drops on all the rectangles, then we're home. And we have our communication complexity. Okay. I'm not expecting this to be obvious, so I was thinking that I would prove this, or at least get to prove. Okay, so suppose that pi is a protocol that solves this lifted search problem. As we said, this protocol induces a rectangle partition, not a cover, a partition, which is not necessarily F-structured. So now I'm going to relax it to something F-structured. So fix a rectangle R. So this is some rectangle living in the partition. It's labeled by some C and F, right? I mean, this is a rectangle. When Alice and Bob reach his leave, they will answer with F. What does this mean? This means that for all x, y in R, we actually have the Gn xy. If I just evaluate the gadget on all the coordinates here, that will falsify C. Okay? Which is already half of, so now we're almost C structured, except we don't know what the rectangles look like outside. Another point is that basically, let me just blow up the rectangles outside. I mean, so A lives, what does A look like? Well, okay, I'm overloading a bit now. Indices and like the variable zi and the index I is kind of overloaded here in this notation. So I know that, namely here, I overload variables and indices. But hopefully this is no confusion. So I know that A and B live in this space. And basically what I'm going to do, I'm just going to take everything on A and B living here, and then I'll throw in, and then I enlarge to pick up everything here. Okay? So I'm going to set A prime to be, here I'm picking out the part of A that lives in var C. This is projection to the indices of the variables in C. B prime in the same way, I project it to the variables. This is the indices of the variables in C. And then for the rest, I just throw in everything. Okay? And now I set R prime to be just A prime times B prime. I claim it's clear that R prime is a larger rectangle. I claim it's clear by construction that R prime is C structured, fulfills condition 2. And since whether I'm violating C or not only depends on the variables in C, property 1 also remains true. So I claim that these are, so if I now, so this means that actually R is C structured. Are you happy with this? Okay, so now we do some calculations. So using what Razborov figured out back in 1990, apparently, let's look at the rank of A. Then I claim that, well, look at all the rectangles in the partition. Okay? And sum up their ranks. I'm claiming just by basic linear algebra, proof by intimidation, the sum of these ranks has to be at least this rank. Okay? We can think about it offline, but basically this is, yeah, this is true. Okay, so excellent. Now look at this. Except maybe adding induced on R is helpful. Now let me instead pick out the rectangle cover. Let me denote this. Like I had a way of turning R into R prime. Clearly, I'm enlarging the rectangle. There's no way the rank could go down. Yes? Okay. So, and now, can I upper bound this? Well, let me actually look at pick out the maximum R prime and look at the rank of A induced on R prime. So this is the largest guy in here. Let me multiply that by the number of rectangles. Are you buying this? Okay. So the rank of A is less than the number of rectangles in the partition times the max rank. And now, of course, what you should do is you should divide on both sides by this thingy, right? And now you know this. Now we have this. Okay. So apparently, the rank measure is a lower bound on the number of rectangles in the partition. But where do these come from? They come from the protocol. And I'm claiming that clearly a protocol that has this many leaves, can we say anything about the height of the protocol tree? Well, it must hold that the communication complexity, if this is the optimal protocol, so assuming that this is the optimal protocol, then clearly, in order to get that many leaves, you need logarithmic height in the number of leaves. There's maybe some rounding here, but actually I'm not rounding, so I guess we're okay. Okay, but this, as we just showed, is log of the rank measure. So this means now that we're getting pretty far from where we started. All I need to do now is to get a handle on this. Right? If we can somehow come up with good matrices, then a good matrix so that when and a rectangle cover so that when I look at induced submatrices and I get significant rank drops, that will give me a communication lower bound. Okay. So let me define for a certificate, for a clause C, let me define the certificate of C is the smallest pi that maps the variables of f to 0, 1, and star. Okay, star meaning you don't assign it. So basically, let's just cert f, which I'm going to write pi also. That's just the unique smallest partial truth value assignment that exactly violates C. Right? It assigns exactly the literals in C to exactly the wrong value. And let me write cert of F to be the collection of all such certificates. This is now a collection of partial truth value assignments. Okay? And then I can say in general, like if I have any total assignment, I can say that it agrees with pi if for the part of pi that actually maps things to 0, 1, alpha and pi are in agreement. Okay? And now, since F is an unsatisfiable CNF formula, any truth value assignment will agree with some certificate. I'm just sort of saying trivialities in this new language. Are we happy with this? So good. So now, here comes the next key notion, and now we're coming to, I think, the contributions of Robert's thesis. Again, F is an unsatisfiable CNF formula as before. Bold F is any field as before. And now, let P be any multilinear polynomial. Multilinear polynomial over the variables z1 up to zn. Then the algebraic gap complexity of F at P, the gap complexity in the field bold F of the CNF formula F at the polynomial P is the degree of P minus, look at all the certificates, hit the polynomial P with the certificate, look at the degree and deduct that. Okay, so it's a kind of similar, we're looking at the degree and then we're subtracting how much does it drop when I hit it with a certificate. And now I can define the algebraic gap complexity of F in the field bold F by just taking the max for all polynomials, supposing that I also want P to have maximal degree. It's a multilinear polynomial, so n is the maximal degree. Okay, so is the notion clear? Like, this is a definition. Do you want to? I don't know. So here's a. So here's an exercise, maybe. Exercise or an example. Let F be Z1, not Z1 or not Z2 up to not Zn, and then a big disjunction of all these variables. This is a CNF formula. Let P be the polynomial that is just the OR. So OR is 1 minus product I goes from 1 to n, 1 minus Zi. Then I claim that the gap in any field of F with respect to P is n. Okay, why? Well, because the certificates, what certificates do we have? we have n certificates here that will just set a variable to true. And for all of those, when I restrict p by standard certificate, this thing just dies and I get a 1. Yes? And the final certificate is the one that sets all of these to true. And then I get a 0, I guess. Or what do I get? Time for this. I think I messed this up. Sorry. The final certificate is the one that sets all of these to false. And then I'm going to have 1 minus a product of load of 1. So I get a. So for these certificates, P just collapses to 1. And for the final certificate, P collapses to 0. Okay? So in particular, if this was our formula, this would be an amazing polynomial that would show a big gap. Okay? Is this making sense? So except why do we care about this? Because of this, that Tony Pitassi and Robere showed that the gap complexity of the CNF formula F in the field bold F is exactly the Nullstellensatz degree of refuting. This requires a proof. And I don't even know exactly how the proof goes. I started reading it. I think this would be, I think this is interesting. And one reason again for why do we care about all of this? So I think this is one of the main contributions as I understand it, with the caveat that I'm not on top of things, but the way I understand it, this is one of the key contributions of Robert's thesis. And because this rank measure can be used to study lots and lots of different computational models, also it turns out that somehow, if you understand this, then if you understand these things, then somehow you can do things in algebra and you can get all of kind of interesting consequences. So what our game plan is now is, so what is our plan? What do we want to do? Well, we want to find some polynomial P witnessing the gap complexity. And then, importantly, we take this polynomial. So this lives in the unlifted space, right? And now the point is, suppose I do the following. Suppose I lift this polynomial. Now this thing is actually an xn times yn matrix, right? So this now is something, this is a matrix, I mean, this is a polynomial that lives in the lifted space. And if I evaluate it at all points, I get a matrix with these dimensions. Are you with me? Like I have to help me here. I don't want to
start at that.
Like why does this make sense?
Yeah.
And why is this true? Yeah, excellent question. I thought about. I think this is really like a separate lecture. I mean, this. I don't think it's obvious. The one thing that I asked Robert about it also. So the one thing it pops out of is that you can sort of. One thing he said, if I understood him correctly, that you view this like, suppose you're looking for a design, then you can sort of try to set up equation systems like, what would my design look like? And then when you do that and the dust settles, then sort of the fact that you have this drop here is sort of that's the number of polynomials your design will be able to take care of.
Does it choose that we are starting with formulas in a non-trivial way? Like, why are we just choosing designs then? That's what I was wondering about.
Because
this makes sense only for formulas, so they're using some.
You mean CNF formulas?
CNF formulas, yeah. So it's not arbitrary.
It's a good question. How much? I think we're. Yeah, I mean, but we know that we are using the falsified clause search problem somewhere because already we're starting everything. We are using a. It's a good question. I don't have a good answer, but we do know. Again, we're sort of in contrast to previous lifting theorems. We know that we are now we're deep inside the lifting theorem that is false in general. Again, Loff and Mukhopadhyay proved that there will be no generic lifting theorem. But where we're at now, we're lifting Nullstellensatz degree lower bound. And you can still, it's a relevant question to say, yeah, am I lifting Nullstellensatz for CNFs specifically, or am I just lifting Nullstellensatz? I think we are using pretty heavily that we have these nice certificates. Is the best answer I can give to this. It's a relevant question that is not maybe getting a great answer. Okay, so where are we? Suppose we have we started with a formula with large Nullstellensatz refutation degree. Hence, it has a large gap, witnessed by some polynomial. Fix it. This polynomial lives in our unlifted space, 0, 1 to the n. Lift it to xn times yn by composing it with our gadget. Okay, and let this be the matrix A. And now we want to argue that A yields a large F-rank measure. If we can do this, we conclude a deterministic communication complexity lower bound. This is what the game plan is from here. And okay, so some just notation. If I have any multilinear polynomial P, then obviously I can write this as just look at all subset of variables. Look at that monomial, and I can look at what that coefficient is. And if you're into Fourier analysis, then it's natural to give the name P hat of S to this coefficient. So let me just do this. I could have called it something else, but this is kind of a natural name. And the lifted polynomial now, the way I define, just to make sure we're on the same page, the lifted polynomial evaluated on xy, or xy living in xn cross yn. This will then just be, if you think about it, looking at all subset of the original variables, pick the same coefficients, but now you evaluate it on the gadget. You evaluate G on xi and yi. Okay. And again, I'm immediately going to overload notation to view this also as the matrix that I get if I evaluate this polynomial on all of these points. Okay, just because if you weren't confused enough, then I think overloading notation makes it sure that I lose you. Okay, so that's sort of that. Or I don't know, but this is how we did it. This is how it's written. And now comes one of the main technical theorems, and this is from the Rezende et al. Paper, but it's basically heavily using what Robere and Pitassi already did. Suppose that the rank of G is at least 2. Suppose that P is any multilinear polynomial, G is any gadget, then I would be interested in understanding, like I want to understand the rank of this matrix. Why do I want to understand the rank of this matrix? Well, because that's the matrix that I'm going to plug in here. Okay? So I would like to understand this, and I'm claiming 2 things. One thing is that this is, in fact, at most, look at all subset of variables such that this monomial has a non-zero coefficient. Look at all such subset, look at the rank of G, raised to the power of the size of the subset and sum them up. This is an upper bound on the rank. Okay. To be clear, this requires a proof. And this is also one thing that, you know, if you're willing to stick around till maybe 5 p.m., then we would do it. But I'm not sure we want to do that. I think we probably don't want to do that. And the point is that, okay, so what Tony and Robert did was to say if G is a very particular gadget, if it's a so-called good gadget, which is high rank but not full rank, kind of, there's a technical definition, then it turns out that this is in fact an equality. This is exactly type. Unfortunately, equality is a full rank gadget, and then we cannot prove this, and it's actually, I think it's false, probably. But the main contribution of the follow-up paper was then to say that, well, if G has high enough rank, then this is almost type. Namely, the lower bound is I'm summing up over exactly the same, look at the same coefficients, all the non-zero coefficients in this expansion. Look at those sets. How large are they? I take the rank of G raised to the size of S, except I adjust by 2. So the rank of this lifted matrix is like sandwiched between basically I can understand this rank by looking at the large coefficients of the polynomial. And now I think we're done. We are about to state our final theorem. Where are we going to do this? Maybe on the middle board. We probably, yeah. Let's see if we can fit it on this board. So I want to give you the, again, this is not super hard, but it requires basically it requires a bit of linear algebra. We could totally have done it. It's just that it sort of took a lot of time to set things up. And I feel that where we are now, again, it would, you know, half an hour to 1 hour more to do this properly. And I think we don't want to do that. So let's just accept this as a magic fact that is true. Then, here comes the punchline. Let me ask of the rank of G something slightly larger. Let me ask that the rank is 3. Why 3? Well, because it's sort of 2 minus 2 is not going to be fun. That's why I want 3. So let F be any unsatisfiable KCNF formula over n variables. Bold F is any field. G is any gadget of rank at least 3. Okay. Then there exists an xn times yn matrix A. And so we already hinted heavily what this matrix should be, but it exists such that for all F structured rectangle covers, the following holds. So fix any F structured rectangle cover, right? Recall that, okay, I guess I erased this now. Remember that we had this we were maximizing over A, so that's why we get to check fix A, and then we were minimizing over R, so this will hold for any R. This rank measure is at least 1 over K, where K is the width of the clauses, times the degree of refuting F in Nordström over this field, times the rank of G, again in this field, divided by the base of the natural logarithm times n, raised to the power of the refutation degree, times exponential in minus 4 times the number of variables divided by the rank. Okay, and so basically we said that, remember that the log of this was a lower bound on the communication complexity. So basically this is greater equal log of this, which is greater equal to log of this, and now you just take a deep breath and you take the log and this pops up. This clear? Okay. So if we can prove this, then we're done. How does the proof go? Here's a sketch. Well, we're going to fix a P such that the gap complexity of F is witnessed by P. So gap FF is gap FF comma P. Okay, we fixed it. And now you already guessed that the matrix A is going to be P lifted by the gadget. Okay. And now we just need to analyze the rank measure, right? So what's the rank measure? Well, we need to analyze the F rank of this matrix. And then we're going to take the max over all the rectangles in the rectangle cover and look at the rank of PGN restricted to R. Okay. Why do we expect this to be large? Like why is there hope? Okay. Sort of getting a little bit ahead of ourselves. So maybe we can do the numerator right away. How much is this? Well, I mean, we know that F has degree n. Okay, and P has degree n. So there is some S of size n that has a non-zero coefficient. So rank G minus 2 raised to the power of n is a lower bound, right? So the numerator is at least rank G minus 2 raised to the power of n. Are we happy with this? Or maybe our level of happiness is starting to decrease a little bit. Anyway, so this is basically, I'm just looking at this, and I'm just using this theorem here that I can understand the rank by just looking at the non-zero Fourier coefficients of I weight. Okay, so that's great. Why is there hope for this not to be too large? Because where do these rectangles come from? They are consistent with, I mean, they come from the protocol. And the protocol identified a falsified clause. And basically, in the lifted space, I have an assignment that projects down to a certificate pi for this clause. And what do I know about how P behaves when I hit it with a certificate? Well, the whole point of gap complexity is that the degree collapses massively. Okay? This is still not making us too happy. I mean, the degree decreases massively. Okay, fantastic. But I want to maneuver into a position where I can use this. And now I'm going to argue that because of structuredness, I will get lifted matrices also in the denominator. So that I'm going to be able to argue that the matrices, all of the matrices here look like this, but that means that I can lower bound them by this. And I know that I have very small, like the largest coefficients here have size n minus gap, which is, I mean, gap is a large number. Okay. So here is the point where the hand waving is getting more and more violent. And the voice is getting more and more strained. But, you know, I trust that what's working in my favor is that you guys want to go home. So you're not going to ask too hard questions. But that's the sort of the game plan, how I'm going to survive from this onward. So what I claim is what we need to show is that here's what I need to show. Take P raised to lift it to Gn and look at it because this is row structured. What's going to happen is I'm basically going to evaluate it on the certificate. Okay, so there's going to be a matrix that is going to be P evaluated on the certificate. And this matrix, I'm just going to get it in a bunch of copies here. And this is because pi is only going to affect, I mean, it's going to freeze how the lifted part that is related to the variable c, how that behaves. And then outside, because we're C structured, we're just going to range, we're just going to pick up like all possible points here. This, just let me be clear, this requires an argument. I'm cheating on this argument. But I'm saying, suppose that you believe this, well, then the rank of this thing is just, I mean, what's the rank of a matrix? This is just a bunch of copies of a smaller matrix. The rank of this. Okay, so in fact, this shows if this is true, then the rank of this whole thingy is just the rank of M. And now we're in business. And I don't think I need this any longer. This is maybe enough for me to. We're getting to a point where we really want to wrap up. So let me see. What can we do? Like, what will the argument be? Well, in that case, if this is true, then let me just copy some facts over here. Then I know that the rank, the F rank of P restricted by any certificate, this is the polynomial, lifted to everything except the variables of C. Just looking, let me plug in this inequality. This is less than summing over all subset of variables such that in the restricted polynomial P restricted by pi, the coefficient of S is non-zero. Right? Look at all such set S. I take the rank of G and raised it to the size of S. And now, obviously, I'm going to use here now that the rank, here is where I want to use that the degree of P decreased massively. Okay, so what I'm going to say, firstly, suppose, let's look at P. So I know that P, the restricted polynomial, has non-zero coefficients only if S is less than n minus, I think it's less equal probably, S minus gap. This I know. And the point is the gap is going to be fairly large. Gap is like n over log n. Okay. Without loss of generality, we can just choose P also so that in the original polynomial, P of S doesn't have any coefficients for S less than n minus gap. If you just think about the definition, you want to have something high degree that collapses to low degree. The whole game is played out in this regime. So monomials of smaller degree, they don't contribute to anything. So let me just truncate all of them away. This is nothing deep, it's just. Yeah. But now I can count how many. So this means that what am I summing here? Well, I'm claiming that S is, as we said, S is in at most this size. And I'm also claiming that S must be, for any S that, okay, so look at any S that survives in P restricted by pi. Any such S must be of degree at most n minus gap and of degree at least n minus gap minus k. Why? Because k is the width of the polynomial, so it's the domain size of our certificates. Okay, and I'm choosing P so that no certificate, that it has no coefficients, non-zero coefficients for degree smaller than this. Okay, and we know that no coefficient larger than this survives, but it could happen that you had coefficients of exactly this size that where the pi hit them but set all the variables to the right value. Right? The monomial where pi actually sets the variables to 1. such a monomial will collapse to degree something like this, or for some I in between. Am I making any sense right now? Some sense? Okay. So then I claim that if we just put this together, we're going to get, so again, we're trying to understand this value. And this is going to be less than, again, I'm summing. Okay, let me actually retype what we're doing. We're looking at all the subset of variables S such that the restricted polynomial has a non-zero coefficient as S. We're summing up rank of G for the set size S. How large can this be? Well, this can be, I claim, just using this, we know that the degree will, let me look at how much the certificate hits S. It's somewhere between 0 and K. The monomials that survive, they started out with having at most gap okay. We know that S has at most this size, and then I'm just going to subtract the i's. And sum up again, rank FG raised to the power of S. And now we're just going to say, well, this is at most K, or maybe K plus 1. I'm actually cheating a little bit here, so let me write something like this. This is at most K, and the largest binomial coefficient here is going to be N choose gap F of the CNF formula F. And then I'm going to get rank F of G raised to the power of N minus gap. Something like this. And now basically just massage this now. Now we have good estimates for this. And we're going to keep this. And then what's going to happen is that what's going to pop out is basically this. You see that because you're going to have, okay, so what's going to happen? This here you're going to get raised to the power of n. Here you're going to have raised to the power of n minus gap. So you're going to divide, you're going to pick up something like, at the end, you're going to get some sum like this, where it says gap here and gap here. This is, if you work on this, then you're going to get an expression that looks like this, but it's going to say gap everywhere here. Okay. And then we just use that, what I conveniently erased, that the gap is exactly the Nullstellensatz refutation degree. So once I get this expression where it says gap everywhere, then I just plug in Nullstellensatz degree everywhere, and I get this, and then I take the logarithm, and then I get this. This is modulo the detailed calculations and some typos. This is how it goes. So what did I cheat you on? I didn't prove the fact that the rank of the lifted polynomial, this matrix is also has been called in literature, this is known as a pattern matrix. I think somehow P is the pattern that is lifted with a gadget. So Shirstov, I think, was the first one who worked on pattern matrices and understanding the rank of pattern matrices. So we didn't argue that the rank of pattern matrices is governed by the Fourier coefficients of the polynomial. This requires a proof, but this is not super hard. And then we argue that the algebraic gap complexity is exactly the same as the Nullstellensatz degree. This, I think, is somewhat deep, and it might be worth talking about that separately, but some other time, not today, because it's already getting too late. So modulo these two things, and modulo that I didn't do these calculations carefully. We saw sort of morally how the proof goes. We didn't do the upper bound, that there are cutting planes proofs in small line space and somewhat short that just pack all the true variables up into an exponentially like large sum of equalities. But I hope this is somewhat believable. And again, I want to stress that this is not technically hard. I think the idea is to really realize that you should pick a whole formula, say a pebbling formula, and then the equality gadget allows you to sort of pack a lot of information about true variables into a single pair of inequalities. That's sort of that's the nice technical idea. And then we were stuck for quite a while because you needed lifting with equality, and as we saw that Loff and Mukhopadhyay proved that is not true. But then it turns out that you can plug in the lifting theorem by Pitassi and Robere. But in some sense, since we know for pebbling formulas, what do we know? We know that decision tree complexity and Nullstellensatz refutation degree and parity decision tree complexity is the same. So one of the things we mentioned in our paper is, in some sense, philosophically speaking, it would be interesting to know what are we actually lifting here. Well, technically speaking, we know that we're not lifting decision tree complexity in general, but are we sort of morally lifting decision tree complexity of CNF formulas? Are we lifting parity decision tree of CNF formulas, or are we lifting? I mean, the way the proof is written, it looks like we're lifting Nullstellensatz, but is that true? And also, I think when I talk about this, something that I maybe said already before today, I would say again. I think by any standard, this is a fairly roundabout proof. At this point, we're pretty far from where we started. And there's precious little insight into like, why does this give us time-space trade-offs for cutting planes with polynomially bounded coefficients? So it would be nice to actually just, have Alice and Bob set up a protocol, deterministic protocol, and could we get some kind of simulation argument where you look at a protocol and somehow knowing more about the problem than it is just a search problem, but somehow maintaining, looking at Alice's and Bob's input and when they go low on some coordinate and do some kind of more hands-on simulation argument. And if you could do that, could we then get a true time-space trade-off for CP star? I think that would be super nice. But I think this is where I will end the lecture.